This is conceptuality13c video. I'm going to put these diagrams, I'm going to make PDFs of them so you'll be able to look at them at leisure. But I just want to go through these and try to get you to understand a little bit more from a very simple perspective about frequency. Okay, and also just some more understanding of the triangle. Here we have two isosceles right triangles. Okay, here's one right here, and here's one right here. Now, our tendency in math and in life is to say that we have a square and that we put a diagonal across the square to make two triangles. But really, that's not correct thinking from our perspective. What we have done is we have two triangles sharing the hypotenuse, which makes the square. It's the reverse kind of thinking, because the square doesn't exist without the triangles. It's not stable. So here we have the really simplest case in the universe of the isosceles right triangle, right? Now, in this case, we called it a three frequency, 1, 2, 3, 1, 2, 3, and this is the picture of since this is a three frequency triangle, because it has three frequency on each side, and it looks like this. So that this is the big one, and we know that there's 9 of them in here. 1, 2, 3, 4, 5, 6, 7, 8, 9 of these in this isosceles right triangle. And so we know that the area is base times 1/2 of the height, which gives us an area of 4.5. Now, if you want to think in terms of squares, it's base times height equals 9. 3 times 3, square aside, you get 9, and the area of one triangle is half that 9, or 4.5. Okay. Now, what this simple diagram does really well is it shows you how frequency is not completely analogous to the way that we think of measurement of division. It's an equal division, but the lengths don't necessarily stay the same. Okay, so in this case here, on the original triangle, we have the hypotenuse. This is this side here, which is the hypotenuse, which for the three frequency is the square root of 18, or 4.2926. Okay, now we, just like in the demonstration we did before with the elastic triangle, we've just moved this triangle over here, and now you can see that this side length went all the way from 4.24 down to 3.16. It went from the square root of 18 to square root of 10. Meanwhile, this one went from 3 here to 36055 here, square root of 13. Okay, so, but the area has stayed exactly the same, and the frequency has stayed exactly the same. The only thing that has changed is the shape, right? So that's an important concept to understand in the difference between frequency and the way we normally think of measurement. This square root of 13 is still divided into 3 equal 3 equal parts, and this one is still divided into 3 equal parts. So this is a 3 frequency triangle, and all the areas are everything else about it is the same. The shape is different, but the areas are the same. Okay, so that is that. Now here we're back to the 3 2 3 2 3 triangle. I hope you can see this, but I'll make a PDF of it. But this really is it shows how we deal with frequency when we have unequal sides. Okay, so that we have a 2, 3, 4 triangle with an area of 2.9, and we know that these formulas, the height is 2 times area divided by base, and area is height divided by 2 times base. Okay. Now, and we're not trying to make mathematicians out of you, or you don't really have to understand the broad concepts that we're talking about in pure conceptuality. You don't really have to get into the detail of this, but I just feel like I have to for credibility. That this is what's happening. Now, in the case of the 2, 3, 4 triangle, and when the base is here at 4, and the height is 1, 4, 5, and we divide always have the height is always exactly the same frequency. It's the same frequency as the base. Okay, so then we have the base of 4 squared makes the 16 triangles that are in the frequency 4 triangle, and the shapes are exactly the same. There's just 16 of them, right? And then when we turn it around, this very same triangle, and we have the base of 2, we then have a height of 2.9, and we also have, we have the area, the same area of 2.9 in this case, but we have a 4 frequency triangle because the base is 2. So now the area of the 1/4 of the 2.9 is 7.25 for each one of the included triangles. Up here it's 1.18125 for each triangle. You multiply that by 16 and you come out with 2.9. And then on this one we have turned it to the 3 frequency side, and that gives us a height of 1.933, and each triangle has an area of 3222. And you multiply that by the 322 by 9, and you get 2.9. So I just wanted you to see that this is how you integrate the concepts of having a different side lengths. This works perfectly well. It's completely rational, but it's a different way of thinking. And I also just wanted to point out in this same diagram that when you have let's say a 1, 2, 3, 4 frequency base of any triangle, and you do when you bring down these vectors from the apex, each triangle is the same area. That's just, it isn't intuitive, but it's true. I mean, these triangles are all equal area because they're the same base of 1, and they're the same height of 145. Okay, now this is, you don't want to get lost in this stuff, but like I said, I'll have it. I'll have PDFs of this. Now here we have an equilateral triangle, and we know that, and it's a 7 frequency, right? We know that we have this is 1, dimension 1, and this is 1/3, or this is the square root of 3 divided by 2, which is 0.8666, and we know that by the base times height, that the area is 43301, right? And the total area is 49 times, because 7 times 7, 7 squared is 49. We have 49 triangles in here. So you can get the same area by this little triangle by dividing the total area by 49, and you get now what's interesting here is that we can start slicing off, boom, 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 boom. We can start slicing off this equilateral triangle, and we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 triangles on this slice here, and we both 13 times 4, 3, 301, and this is the that area that we're taking off. And we do that go down each line, boom, 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 boom. And these are the areas that we're taking off of the equilateral triangle. When you subtract the smaller from the larger, as we go down each time, each place, it comes down to exactly 8.66, which is the height of an equilateral triangle. So that's pretty, this is, I think, interesting that these relationships, when you study this a little bit, and it's not necessary to totally understand this in detail to really be familiar with the broad concepts that we're presenting in pure conceptuality. That this is just kind of backup detail that you don't really have to totally understand to realize that the concepts that we're giving are supported by these truths that, when looked at in more at closer range, are rational and figured out. I mean, it all works. Okay, that's it.